Let's step back a moment here and dive into our Ethernet frame structure. Let's think back to the OSI model, layer 2, the data link layer, TCP/IP stack. That's the network access layer. We have a frame that has to be created. This is the frame right here. Now, Dan, we have at the beginning of this frame a preamble. What's this preamble all about? How important is this preamble?
Well, I know one preamble, and I believe it begins, "We the people," but this is not that. This is better thought of as a warning shot, and I wish my wife did this. My wife will sort of interrupt me when I'm doing something else and begin talking to me, and my brain won't really be focused on her. I'll still be focused on the football game, the computer game, the book that I'm reading. And sometimes I don't even know that she's talking to me. And it would be nice if she said, as she's learning to do because of challenges, it would be nice if she just said, "Hey, Dan, I'm about to talk to you. So get ready. Tune in to me." That's what the preamble is going to do. It's a warning shot to prepare the Ethernet card that something is about to arrive that they need to pay attention to.
Dan, we've been teaching this a long time. It's not the first time we've used that example. I told my wife about this example, and I ran into that situation where I was focused on my task, that she was talking to me and I missed the first 5, 6 words. So what did she do? She goes, "Preamble." And then she starts talking to me. So, yeah, it worked. I looked right up and I immediately started to listen. So, that's great. So that's what we have here. Get ready. A frame is coming. And then we have this SOF, a start of frame delimiter. And all this is saying is, here's the beginning of the frame. It starts right now.
In looking at this graphic, we need to understand what those numbers that are dangling above these fields represent. 7, 1, 6, 6, 2. What is this? It seems pretty odd to just put some random numbers above these fields. Well, wait a minute, though. Headers have predefined sizes for the fields that exist within them. And the way that we normally break up a field is on byte boundaries. We don't like to have individual flags too often because it's hard to read them. Certainly computers can read them, but it takes some actions in order to strip down and look at a single bit. Whereas reading a byte, the hardware is prepared to do that. So I see 6 for destination address, and I think to myself, they're looking for an address that is 6 bytes long. Let's do a little bit of down and dirty math. 6 bytes. Raymond, how many bits are in a byte?
There are 8 bits in a byte.
So if we do some multiplication, 6 for the 6 bytes above times 8. We do the arithmetic, and we get 48 bits. So that's a 48-bit field, Raymond, for destination address. What would we expect to find there?
I'd expect to find a MAC address. A MAC address is 48 bits long. So we have our destination address, who we're trying to reach in this Ethernet LAN. And then followed by that, we have our source address, also 6 bytes. It's another MAC address. That would be the sending device's MAC address. So this is where we find our MAC addresses in our Ethernet frame. And then we got a length. Length of what, Dan?
Length of the frame. The frames can be small when we only need to communicate a little bit of information. They can be large, as we would expect if we are doing a file transfer where we want to maximize what we can jam in there. And let's talk about that. So now there's a minimum and a maximum container inside of this. The minimum is 46 bytes. That is, in fact, the minimum packet size that we would put when we are encapsulating into that. So think about it. This is the wrapper on top, outside of the packet.
Dan, you just said packet. Let's remind everybody where we find that packet. We come down our model, we get to layer 3, the network layer, or the internet layer. There's our packet. So what we're talking about is taking that information and sticking it in here. The smallest size is 46.
So, folks, what would we say for the maximum packet size, which is called the MTU, maximum transmission unit? What do you think it is, based on this graphic? It's 1,500. Now, there are ways of getting this bigger, and you may know about them. Jumbo frames. Jumbo frames can redefine the MTU on an Ethernet LAN. Certainly possible. Sometimes, however, we'll expect an MTU of 1,500. Our Ethernet card may be programmed by default with an MTU of 1,500. We might get a frame received that has some extra headers that we're not prepared for. And we would consider those giant frames. A giant frame is not a good frame. It's a frame that exceeds what we expect, and our expectations are based on the MTU. There's also runts, not to demean frames, but anything that is smaller than 46 for the minimum transmission unit would be considered a runt. Lastly, we have that FCS, and we talked about that earlier when we were dealing with the encapsulation of the frames, the OSI model. Frame check sequence. It's a mathematical check on our frame to validate that no corruption has occurred.
The MAC addresses we find inside of our frame can come in many different flavors. It can be unicast. It can be broadcast. It can be multicast. And depending on this flavor, will determine how we communicate on our local area network. For unicast communication, we are dealing with a one-to-one communication. Dan, when I say one-to-one, what are we referring to?
One station talking to another station, or one host talking to another host. It might be you're setting up to your default gateway, the router. It might be that there's a printer on your network and you're sending a print job directly to that device. And this is really the normal modality of communication. Make no mistake about it. Unicast sounds strange. We'll talk about broadcast and multicast a lot. And so you'll cease to remember what unicast is, but that's normal. One-to-one communication. So what are these abnormal communication modalities? And it's not that they're abnormal, but they're a little bit different. And they take some getting used to. Broadcast. Raymond, we've in fact used that term a few times. Let's really give them an understanding of what a broadcast is.
So a broadcast MAC address means that we are communicating from one device to everybody inside our local area network. One to everybody. When might we have to do that? When I'm sending out an ARP request. I'm trying to find the MAC address that is associated with an IP address I already know about. When I send out a DHCP discover message. I'm trying to contact a DHCP server. I don't know where they are. I have to broadcast in order to find that DHCP server. Dan, is there a specific MAC address associated with broadcast communication?
When we broadcast on Ethernet, the way that we trigger that is to put in a destination MAC address of all Fs. Now, F is in reference to the hexadecimal maximum value we can have. You can't have a number bigger than F. I know it's a letter, but in hexadecimal, that represents 15. You can't have bigger than that. And that's the most common way that any mechanism is going to broadcast. It just maximizes everything out, and it goes, I'm shouting. Kind of like you're pressing caps lock, maximizing the size of your characters. So here, when we broadcast, we use the MAC address of all Fs. But now I'm beginning to question something, Raymond. we have two fields for MAC addresses. We have a source and we have a destination. Destination comes first. So where would I encode this all Fs MAC address? Would I do it just for the destination or for both the destination and the source at the same time?
It would be just the destination, Dan. The source MAC address we know. It's our MAC address. So the source MAC address would be mine. The destination would be all Fs.
So regardless of the type of communication, you always put in your own MAC address when you're sending and initiating traffic into a broadcast domain. If you do anything else, you're hacking the network, you are spoofing MAC addresses, which is possible, but it's not a good thing. It's not a good thing. So we've covered a few, Raymond. Unicast, one-to-one. Broadcast, one to everybody else. Send to all Fs.
Our last one is multicast. What's multicast? It's communication from one to a group of end stations. A group. A specific group that is subscribing to that communication. So Dan, when might we utilize multicast?
Well, there's a few times. When we're talking about multicast that just communicates inside of a single broadcast domain, I think about the fact that I can multicast to all the routers. There's a multicast address for that. There's protocols that rely on multicast communication. Spanning tree protocol, CDP, OSPF, EIGRP. When we communicate these multicasts, we put in and encode a very specific MAC address that is recognizable as multicast, and then when we're running that service, if we're running CDP, we're subscribed to that group. When we're running spanning tree, we're subscribed to that group. So our network interface cards are looking at frames that come in. They see the bits, they see frames that are presented and came in from those bits, and they're looking for frames that are destined for their MAC address, for the broadcast, and also for any multicast groups that we've subscribed to. That's the term Raymond used, subscribed. And there's even more advanced approaches where we might subscribe to video feeds, a video broadcast in our organization where the CEO, the president, our leader is sending a video broadcast, maybe about financial information that trickles through the entire network. We subscribe. We say, I want to latch on to that video feed. And it's much more efficient than broadcast. Much more efficient than broadcast. Broadcast is still a necessary evil on Ethernet. And we don't want to eradicate it. But when we have the choice as protocol engineers, we're not really protocol engineers, we'd prefer to do things via multicast as opposed to unicast, or multicast as opposed to broadcast. Broadcast, not so good.
Let's open up our MAC address. Let's see what it's all about. Dan already mentioned that it's 48 bits long. But these 48 bits, we can break that up into two different sections, 24 bits each. The first 24 bits are known as the OUI. OUI. Not IOU. I don't owe you anything. Dan, what does OUI stand for?
Oui in French. But here, it's the organizational unique identifier. Do we really care? Not that much, but the OUI is the portion where a vendor gets assigned a block of space to build their own gear, their Ethernet gear. They would have NICs. They're assigned these OUIs so that the OUI for maybe Raymond's organization is different than mine. If we're manufacturing Ethernet gear, that is going to minimize and hopefully eliminate duplicate MAC addresses. We don't want duplicate MAC addresses. And if we do, in fact, have a duplicate MAC address on the exact same broadcast domain, the exact same Ethernet LAN, then everything becomes squirrely. An assumption of uniqueness can no longer be relied on, and we're going to start to get a lot of error messages. So Raymond, I have my OUI. I got that. I'm building Ethernet cards, manufacturing them in my factory. But how do I get that true uniqueness? The OUI, I've got to keep it fixed. So how do I get uniqueness?
You have another 24 bits to play with. The last 24 bits is the vendor-assigned portion, meaning that you get to create the remainder of the MAC address utilizing these 24 bits. So you can be pretty unique here. And the odds of you creating duplicate MAC addresses and those duplicate MAC addresses ending up in the exact same LAN is very, very slim. Remember, the MAC address has to be unique, but it has to be unique within that local area network. So it's possible to have two network interface cards with the exact same MAC address out there. As long as they're not in the same LAN, it'll work.
When are you most likely going to get duplicate MAC addresses these days? I'd say cloning virtual machines. When you clone a virtual machine, you clone the whole thing, including the MAC address. And if you put those virtual machines in the same LAN, you're going to start to get some error messages. One useful thing about the OUI before we leave this is if you are troubleshooting something and you notice that there's perhaps an offending device and you're trying to figure out the whereabouts of it, glean more information about it, if you know the OUI, you could look that up and you could go, oh, that's 3Com, Intel, Cisco, and potentially narrow down the possible devices that might own that. I've also seen people use that to find the right drivers for an Ethernet card. Thankfully, our operating systems are a lot better about having the right drivers. That is, except for server operating systems. Server operating systems tend to have a smaller driver set to pull from, and you might have to do a little bit extra work, and maybe that's going to aid you. Knowing the OUI, find the vendor. I didn't even know that that was a Broadcom card. It didn't even say it on the card itself, that PCIe, PCIX, PCI card. So that's the big use. Oh, Raymond, let's not lose sight of the size of this. We've already said it, but how big is a MAC address?
48 bits. We have to remember that. What is Cisco's OUI? Does it matter to us? Not really. But they were pretty lucky. They got 5 zeros followed by a C. Pretty cool. But is there a standard out there for the format of a MAC address? No. There is nothing whatsoever in regards to a standard. Look at these different options here we have. Dan, do you see similarities besides just the hexadecimal values?
So we can have a separator of a period, a colon, a hyphen. The convention is if we are using periods to separate, we're going to have 4 hexadecimal digits, and the other representation approaches are going to take 2 hex digits, basically a byte, because a hex digit is a 4-bit field, and then separate them out. But there's even a 4th way that we represent them without any separators. If you go into your Windows operating system, your driver, and you want to change your MAC address, well, generally you do not put in any separators. And you might be doing this to satisfy uniqueness of multiple virtual machines that you're plugging in to an Ethernet LAN. So the reality is, all we want to do is we want to make sure that our MAC addresses are unique. There is one time we might adjust this on a Cisco router, and that is if maybe our service provider is expecting a MAC address and they've somehow coded their side to only communicate with this MAC address. We may, in fact, want to discover what our old MAC address is and encode that in potentially replacement gear that we put in to fix a potential outage. So MAC addresses, nice to be familiar with them. Oh, Raymond, how do we determine these on a PC? If I'm on a PC, Windows, Vista, 7, 8, XP, how do we determine our MAC address?
Well, we have to make sure we use the right command. If we type in ipconfig, that only shows us IP address, subnet mask, default gateway. We need to tack on the switch all. So ipconfig space /all. Hit enter. And as we go through that information, we'll see physical address listed.
Wait a minute, Raymond. Something is amiss here, is it not? We have it has to be a MAC address. But Raymond, I know the MAC address to be layer 2. I know it's our physical address that lives at layer 2. Ooh, I spilled the beans. So we can call it a physical address safely, accurately. It doesn't live at layer 1 of the OSI model, though, does it? It lives at layer 2. So we could call this the data link layer address, the MAC address, and from this output, there's nothing wrong with it. It is okay to call it the physical address, even though it is not layer 1.